Homeowners and contractors usually ask me this question. We want to open concept design. We want to remove this wall here. How far can the beam span? Should it be wood or steel? Is 7 meters too long for a beam? In this video, I'm going to engineer this step by step and show you what actually controls the answer. I'm a licensed structural engineer in Ontario. I work mostly on residential renovations, wall removals, and beam replacements. Let's walk through how an engineer evaluates this problem. We'll assume a simply supported beam with a span of 7 meters. This is the plan view. And this is the beam that we're going to design. The tributary area is from here to here between these two lines. This is the tributary area. And tributary width is 4 meters. For loads, we'll assume a typical residential floor, a dead load of 10 psf, pound per square foot, and live load of 40 psf. For strength design, we use factored loads, 1.25 times dead load plus 1.5 times live load equals to 1.25 times 10 plus 1.5 times 40 gives total factored load of 72.5 psf. That converts to 3.47 kilopascal. 3.47 multiplying by the 4 meter tributary width gives a factor line load of 13.9 kilonewton per meters. Now we have to calculate maximum bending moment and shear. Maximum bending moment equals to W times L squared divided by 8 equals to 13.9 kilonewton per meter linear load multiplied by 7 squared divided by 8. That gives 85.1 kilonewton meter maximum moment. Now shear. For shear, we have W multiplied by L divided by 2 equals to 13.9 multiplied by 7 divided by 2. That gives us 48.6 kilonewton of shear. Now it's time to size the beam. Let's try LVL beams first. So we're gonna use LVL 1 3/4 by 11 7/8. To obtain the bending and shear capacity of this LVL, we should go to the manufacturer's design tables. I bring an example here. You can see for 11 7/8, this part of the table gives us the information that we need. This is in imperial. We have to convert to metric first. So it's going to be 23.9 kilonewton meters for moment. For shear, it's going to be 30.72 kilonewton. And for moment of inertia, it will be 101.56 times 10 to the 6th. That is the moment of inertia, millimeter to the 4th. These values vary by manufacturer, so you should always check the manufacturer's design tables. To resist 85.1 kilonewton meter, we need at least 4 plies. 4 times 23.9 is 95.6 kilonewton meters, which exceeds the demand. Shear also checks out. So from a strength standpoint, the beam works. But strength is usually not the controlling factor in residential beams. Now we need to check deflection. For deflection, there are usually two common checks. One for live load, often L over 360, and one for total load, often L over 240. Different projects and standards can vary, so always confirm the applicable criteria. L over 360 equals to 19.44 millimeters. L over 240 is 29.16 millimeters. To calculate the maximum deflection, this is the formula. Delta maximum is 5 over 384 times WL to the fourth over EI. So we're going to calculate the maximum delta for once for live load and once for live load plus dead load. To do so, we need to calculate linear load for live load and also for live load plus dead load. So for live load, we have 40 PSF. That is the live load we have, which is equal to 1.92 kPa. 1.92 times 4, which is the tributary width, equals to 7.62 kilonewton per meter. Live load plus dead load, we have 50 PSF, which equals to 2.4 kPa. 2.4 times 4 equals to 9.6 kilonewton per meters. This is 7.68. To calculate the maximum deflection, you can easily use our online tool. I'm gonna put the link in the description below. So using this tool, we can easily calculate the deflection for live load, which is 42.87 millimeters, and also for live load plus dead load, we have 53.59 millimeters. 42.87 is greater than 19.44, and 53.59 is greater than 29.16, so the beam does not meet deflection requirement. Not good. This would result in a bouncy floor and likely cracking of finishes. To reduce deflection, we need more stiffness. One option is increasing the moment of inertia by using a much deeper LVL. For example, 4-ply 2x16, which is generally impractical in residential construction due to ceiling drops, is checked only as a comparison. 4-ply 2x16. With this section, deflection drops significantly and approaches the allowable limit, but the depth makes it unrealistic for most homes. Another option is using steel. Steel has a much higher modulus of elasticity, so for the same deflection limit, the required moment of inertia is much smaller. We have about 13.78 gigapascal modulus of elasticity for LVL beams, which is much smaller than 200 gigapascal for steel. Using the beam tool, the required steel moment of inertia is approximately 64 million millimeter to the fourth. Looking at the standard steel sections, several W shapes meet this requirement. We can use W250 by 45 or W310 by 33 or W410 by 39. You can use this online tool that we have. I'm going to put the link in the description below. Here you can choose W sections, and below you can see section properties. Here is the moment of inertia. The problem, however, with the steel sections is weight, installation inside an existing house, lack of crane access, and ceiling drops all become practical challenges. So challenges are weight, installation, lack of crane access, and ceiling drops. This example shows that a 7-meter span with a 4-meter tributary width is technically possible but often expensive and impractical in residential construction. In typical residential floor conditions without intermediate supports, spans beyond about 5 to 6 meters usually require very deep beam or steel sections. Adding an intermediate support, such as a column at a kitchen island, can dramatically reduce beam size, deflection, cost, and installation difficulty. Structurally, this is often the most economical solution. One final point. Passing deflection limit does not guarantee a comfortable floor. For long spans, vibration and natural frequency can still govern, and more advanced analysis may be required. So the takeaway is wood can span far, but not always practically. Number 2, steel is not a magic solution. Number 3, strength is rarely the controlling factor. And number 4, deflection and serviceability usually governs. This is why beam sizing should be engineered, not guessed. If you want more simple explanations like this, subscribe to the channel. This is Reza from Sepco.